Hello, welcome, and thank you for joining us today for the Embodied Carbon Network's 2019 webinar series. My name is Kate Simonin, and I direct the Carbon Leadership Forum at the University of Washington, and I'm co-chair of the Embodied Carbon Network. This is the fifth session of a six-part annual webinar series, and we have several exciting speakers joining us today, and that will be outlining how we have integrated whole building LCA into projects and created a new tool for quickly optimizing embodied carbon reductions in concrete, and are taking steps to further define baseline buildings for projects pursuing LEED. Please note that this webinar is being recorded and will be made publicly available upon its completion. Many of you joining today are already members of the Embodied Carbon Network. We do have guests in the audience and who we invite to learn more and join the network. The Embodied Carbon Network is a communications and knowledge sharing platform that was launched by the Carbon Leadership Forum and partners in January of 2017. The network brings together professionals working in or with the building sector together to share news and resources, engage in discussion, and develop educational content. And we have evolved into a vibrant, engaged global community. And today we have over 1,000 professionals from across the building sector. I'll note that it was 1,000 last week, and if we check it today, it's 1,100 and something. So we keep going up every day. So welcome. We have representatives from building sector, academia, nonprofit, and government of over 200 cities and 33 countries across the world. And we're brought together under a shared mission to eliminate embodied carbon emissions in the built environment in order to meet global greenhouse gas emission targets by 2050. The network comprises 10 subject-specific focus groups, which members can join for additional engagement around topics related to embodied carbon. The Embodied Carbon Network is funded and managed by the Carbon Leadership Forum. The Carbon Leadership Forum unites architects, engineers, contractors, material suppliers, building owners, policymakers, and other industry leaders around a shared goal of eliminating embodied carbon in building materials. And through this group, we pioneer research, develop resources, foster cross-sector collaboration, and incubate new approaches to accelerate transformation of the sector, with the goal to radically reduce and ultimately eliminate embodied carbon. So thank you so much for the sponsors of the Carbon Leadership Forum for supporting the Embodied Carbon Network, one of the key places that we see this cross-sector collaboration and discussion happening. So again, today's webinar is the fifth session of a six-part series. Each topic is based off of network focus group topics, and network focus group chairs have worked with their groups to identify speakers and develop the curriculum for each session. Our goal is that each session will not only be useful to the live participants, but also serve as free educational resources for anyone interested in learning more. Please feel free to share the webinar recordings with your colleagues, professional networks, and students. So just to note that where mentions of trade names or commercial products does not constitute an endorsement or recommendation for use, and the opinions, ideas, and products of the speakers on the session do not necessarily represent all of the members of the Embodied Carbon Network or endorsement by the Carbon Leadership Forum. Our goal is to introduce topics that could help participants think and talk about building industry strategies for reducing carbon emissions attributed to building materials. So a few key logistics. We're running this as a meeting rather than an official webinar, so everybody is placed on mute. Please keep yourself that way. If you have questions, please send them through the chat section. We will follow the presentations with a 15-minute question and answer session, and that the moderator will then ask the questions of them. So if you're an AIM member and need any educational credits, this course is eligible for the live attendees to receive credits, and please email us if you fit into that category. And if you missed previous webinar sessions, you can see the website link there to find those resources. Stay tuned for more information on upcoming webinars. You can save the date for session 5, which is happening session 6, excuse me, and December 13th at 9 o'clock in the morning. And there is an all materials focus group call on December 6th. So we have 2 calls coming up in the December. So I'd like to pass over and introduce to you Megan Lewis. Megan Lewis is the chair of the Buildings Focus Group. She manages the materials program and the WeWork Global Sustainability Group, and she has been responsible for curating this session and will be moderating it. So Megan, I hand it over to you to introduce the other speakers.
Thanks. Thanks, Kate. Good morning, everyone. So we have 4 great speakers that are joining us today. We're going to start out with Raphael Sperry, an associate at Arup. He's going to talk about the SFO airport whole building LCA, and then Anthony Pak, an LCA consultant at Preopta, and then we'll move to Baha Sadruddin, who's going to share some of the work they've been doing at ZGF, including an exciting new tool we'll get a short live demo of, and then we'll wrap it up with Victoria, who's going to talk about setting up the baseline for building enclosure and structure for pursuing LEED with LCA. And I'm going to do a more in-depth intro of each of these before they begin speaking. So for now, I'm going to stop sharing and pass it off to Raphael.
I've got to unmute myself. Okay, everybody seeing our screen?
Yeah, and Raphael, let me just give everyone a quick intro on you. So
Thanks.
Raphael is a sustainability consultant for buildings and a leader of Arup's San Francisco energy and sustainability team. He has facilitated the design and low energy buildings and applied the LEED rating system to numerous commercial and institutional building owners, as well as pioneering sustainability applications in transportation projects, especially airports. He contributes to Arup's efforts to incorporate the UN Sustainable Development Goals into their business practices and building projects. He's also president of Architects, Designers, and Planners for Social Responsibility, where he advocates for human rights in the built environment. He lives and works in San Francisco. So thanks for joining us, Raphael. I'm going to kick it off.
Thanks, Megan, for the introduction. And it's an honor to be here with the other speakers, and thanks everybody for joining us for today's talk. So I'm going to walk you through some of the results of the whole building lifecycle assessment that we did for boarding area B at the San Francisco International Airport. So this is kind of an overview of the project. Boarding area B is this arm here. So it's replacing a previous set of terminals that were kind of in the same area. It's about a 500,000 square foot project with 3 levels, 28 gates for airplanes, the $1 billion project, and airport projects do take a long time to construct. It has to be built in pieces, so it's not to allow for kind of ongoing continuous operation of the airport. But on the interior, it's got, kind of elegant and contemporary feel, but probably familiar to anybody who's been in an airport. It's kind of, a long hallway where you've got gates and you've got concession areas, and then down below there's service areas, and on the mezzanine level in places there are passenger lounges. So in the SD phase, we used 2 different approaches to look at the kind of where we could make improvements to the building to reduce its embodied carbon. So we used Tally for structure because the structural engineers were using Revit. And as I'll go into a little bit more detail, the architects were actually using Rhino for modeling the interiors. So it was pretty instructive actually just to export the Revit model. And Tally asks you need to put a picture on the cover, and we used this picture. This building has a tremendous amount of material in pilings, which is what you can see here. The first floor of the superstructure is concrete, and then there's steel structure above. So you say, well, this is a 3-story building, and 2/3 of it's steel. You'd think that steel, which is green down here, would be the larger section of the building's impact. But actually, because of this extensive amount of piles, because the site is very weak soil, which is typical at airports, we have a lot of driven concrete piles. And so the concrete, which is the yellow materials, is actually a much bigger share of the global warming potential of the project. So we're looking at Tally. The other thing, and I'll get this is kind of the output, and what we saw was kind of just looking at the structure alone, because we couldn't add it together exactly, but looking at the structure alone, reducing the cement mix, this is here, with this gray color, has big impacts on the structure in terms of reducing its impact across all of the impact categories that Tally analyzes, which are those from the Tracy tool. So improvements in acidification, eutrophication, global warming potential, which is usually the one that's of greatest interest, ozone depletion, smog formation, and energy demand. That was kind of what we saw that we could achieve with improvements in the cement mix for the building. Then we also had, we did want to look at other opportunities in the building. And as I mentioned, we didn't have Revit information on interiors in SD. So we exported material quantities from this Rhino model here to get square footages, and then we multiplied them by densities and typical thicknesses in order to actually get impact of the different interior materials that were being modeled here. So things like interior walls, flooring, ceilings, and even some of the enclosure as well. And this is just a couple of examples of what we did in that data set. So using those takeoffs, we used a data set that was called a Quartz database. And Quartz uses information from ThinkStep, which is the same vendor that gives information to Tally. So that was really good for this analysis, because when you start pulling in LCA from different kinds of sources that aren't using the same rules, you can end up with results that really aren't comparable to each other. So we felt that at least that was consistent. Unfortunately, since then, Quartz actually got discontinued and rolled into the Pharos database, which really focuses much more on the healthy materials questions that people have coming out of LEED v4 and what have you. So I wouldn't say you could really replicate this approach anymore. But you know, you can also do it directly in Tally if you have Revit at the beginning of a job. And kind of what you can see is flooring in here is yellow. It's yellow in both of these two cases. And in the base case, when we were looking at epoxy terrazzo, which actually is the design that's going ahead, there are pretty significant impacts from the flooring in eutrophication and ozone depletion, smog formation, and so on. And that by, say, replacing epoxy terrazzo with linoleum, you could virtually eliminate those impacts at the scale of, you know, the whole building, which is a great, you know, which was an option. And it was the kind of information that we were trying to find in SD. We didn't end up going that way. And I think that has to do with kind of the need for a particularly hard and durable surface with really, really high traffic areas and that you get in airport terminals. So we unfortunately, even though the impacts are larger, in this, you know, there's other reasons outside of kind of the 5 impact categories that you get in LCA to make material decisions. So moving into, so that was kind of SD. You know, we looked at a couple different options. We said, yes, in structure, we can really get a lot out of focusing on the concrete, and then on the interiors, those are smaller factors, and we kind of looked at some, and the decisions came out based on other factors. Moving into CD, it was time to kind of document the building for LEED, and so we had to kind of look at the mixed concrete mixes in great detail. And this is kind of some of the reports that you get through the structural engineer for the project and from the concrete subcontractor in their submittals about how much cement, fly ash, aggregate, and water is in each of the mixes that you're using. And of course, we had different kinds of, the trick here is concrete's not just one material. There's a concrete mix for foundation elements, which need 5,000 PSI. There's a concrete mix for slabs and beams. There's a concrete mix for a topping slab that's different. There's concrete mixes for columns. There was, I think, about 10 different mixes on this project. So we needed, I think if you want to be precise, there's actually even more, but we were able to kind of round them up into 10 mixes for the Tally model. And then you go to Tally and you open up the material dialogues that you have there, the material assignments, and you can go in there. This one actually, sorry, I didn't get the right screenshot on here, but you can edit for concrete the actual mix design, put in the ratios that you had there, you know, fly ash, aggregate, water, cement, and so on to come up with reports. And this is the kind of report that Tally gives you. And one of the things that was challenging about this project, and not a huge challenge, I'm sure most of you could work your way through this the same way that we did, but that Tally is set up to give you comparisons with those 2 columns for each thing side by side using Revit, where you've used design options to that feature of Revit to model the design case and the baseline case. And in our case, the architects weren't using design options at all, and it didn't really work out for us as a third party, or, you know, a consultant, sub-consultant to them, to try and turn on design options in their model. So we actually ended up duplicating their model and then changing the concrete mixes in the second one. And then because Tally gives you this output always scaled to 100%, we have, you know, 100% bars, and then we have another set of 100% bars for the design case. You can see that in the pie chart kind of over here, the amount that's concrete, which is the kind of yellow tan color here, which is well over 50% in the baseline case, has shrunk. What you can't really see is that the whole pie is actually shrinking because of that strategy, right? But that's what's happening. So we exported to Tally. Tally gives you XL, and then you can kind of build, you know, put the 2 ones side by side. And this is a more complete Tally model of the structure and enclosure. And in this case, the enclosure is the same in both cases, but you need to keep it in there so you can see what the relative savings is of everything. And again, you can see across all the impact categories, things are getting better between, say, the typical case and the low cement case for acidification, typical, and low cement for eutrophication, typical, low cement for global warming potential, where most of our attention is usually focused. And you can see it's because of this orange color getting smaller, the same stack as the same one on top of it, and that's cement. So the final step is to just output numbers for that. And you can kind of, because, you know, these bar graphs don't tell the whole story in quantitative terms, and you can see the global warming potential was reduced by 11% overall. So what that shows you is for the entire structure and enclosure of the building, the low cement strategy just applied to the cement portions of the building was able to reduce the total by 11%. You also want to check for LEED that none of these numbers are actually increasing. And we see that actually none of them are, and actually we're getting pretty good decreases in acidification and smog formation as well, and smaller decreases in some of these others. So I think that suggests that low cement concrete is a pretty no regret strategy. You're not going to end up kind of causing unwanted substitutions by bringing in, say, fly ash, which was the main substitutor here, when you're looking to reduce embodied carbon through a concrete strategy. So that was the outcome that we had. Megan, back to you.
Oh, thank you, Raphael.
Yeah.
All right, so while Anthony is loading his slides, I'm going to give him a chance before I introduce him, and just remind everyone that if you have questions that you think of as these speakers are going through, just put them in the chat box. All right, so now I'll introduce Anthony Pak, who is the principal at Preopta, one of the first firms in North America to provide parametric life cycle assessment consulting services for buildings. He is also the founder of EC in Vancouver, the first local chapter of the Embodied Carbon Network, which organizes local events that empower building industry professionals to champion the topic of embodied carbon on their projects and within their firms. Anthony serves on the technical committee for the National Research Council's Low Carbon Assets through Life Cycle Assessment, or LCA Squared initiative, and he has a master's in industrial ecology from NTNU, a leading LCA research group in Norway, as well as experience completing a range of whole building LCA studies using software tools such as Athena Impact Estimator, Tally, and One-Click LCA. So with that, Anthony, take it away.
Great, thanks, Megan. Hi, so today I'm gonna give a quick presentation on an office building project that was pursuing LEED, and we used a Revit model for this, and I modeled it in One-Click LCA. I can't get into the specifics for the project for confidentiality reasons, but I can just kind of share generally about the results and what were the design strategies and how we modeled it. So in this case, for this building, it's a office tower, or well, like a 10-story office building. And it has post-tension slabs. So that was one of the major sources of reduction, and also the changes in the concrete mixes. So when we look at what led to, the reductions in the global warming potential and the other environmental impact categories, the main sources were first on the concrete mixes. So here I'm showing you, for all the various different building elements for this building, what the baseline assumptions are, which is I'm using the CRMCA, the Canadian Ready Mix Concrete Association's industry average benchmark, which assumes 10% substitute cementitious material, so like fly ash or slag. That's their typical assumptions there. And then on the right side, this was the actual concrete mixes for each of the different elements. So you can see these numbers, 15%, 30%, depending on the various different elements, it's a bit higher than 10%. So that's where you get some of the reductions. And one of the other interesting things was for the post-tension slabs. For this building, given that there was a previous project that was done by the same team, and it was conventionally reinforced slabs, they could actually compare. So I got a letter from the structural engineers where they basically stated what the equivalent slab thicknesses would have been in the conventionally reinforced. So for certain slabs that were 11 inches from the previous project, in this case for the post-tension slabs, they would drop down to 9 inches, and then similarly for 15 inches, drops down to 12 inches. So that reduced obviously the concrete volume there. I still use the same assumptions for the amount of steel in the rebar or the PT tendons. I don't think that there's actually any EPD data for PT tendons right now. So I just assumed that there was no changes in the rebar or the steel quantities on that front. Now, in terms of how we modeled it, we used, so One-Click LCA has a Revit plugin. However, I don't actually have a Revit license. So they actually have a separate tool that's called, what's it called? It's based off of a program called SimpleBIM. And so if you don't have a Revit license, what you can do is you can ask the design team to export that Revit model into an IFC format. And then you can import that IFC format into this tool, where you can then work with the BIM model and map all the various different building elements to One-Click LCA's big database of EPDs and whatnot. Now, when we're because they actually have a pretty big database of EPDs, sometimes it can be a little bit confusing initially. When I was setting up the modeling or the mapping of the different material items, I put an emphasis on trying to find the industry average EPDs for each of the respective materials. And so it's worthwhile to kind of familiarize with that. And I think that may make the results more comparable with results that you might see in other tools. For instance, with Athena, I think most of the data there is industry average data. The other thing I noticed, this was just something that did affect the results, is they have, you can actually change the transportation distances and the transportation modes for all the different material types within One-Click LCA. And for concrete, their default assumption was 200 kilometers, which is actually quite a bit higher than the assumptions that I think are in Athena. So just looking through Athena's user guide, I saw somewhere in there mentioned 40 kilometers, and that reflects closer to the reality for this project. So I changed the transportation distance, and given that concrete tends to be a pretty big impact item, and there's a lot of mass there, transporting that amount of concrete, if you go from 200 to 40 kilometers, it does affect the results. So this is just some of the final results. This led to about a 15% reduction on the global warming potential. And most of the other impact categories are above 10%. So this could hit that 3-point threshold for the LEED credit. One thing I should mention is that they also, within One-Click LCA, they have this Carbon Heroes benchmarking program. And so you can actually, they create this letter grade depending on the kilogram of CO2 per meter squared of floor area. And so in this case, you can see the final, or the baseline building was 737, and then the proposed building was 627. And I've noticed in general, the results are a little bit higher than what I've seen in modeled in, for instance, Athena. But then again, I'm not sure what the source of that is. It could also be that by mapping it from the bill of materials from the BIM model, there's a lot more details that's actually being captured there that may not necessarily be captured when you're approximating using the assemblies within Athena. And then again, you can see the breakdown of where the reductions happened here by different building elements. So most of it came from the floors. The floors accounted for about 11.6% reduction. This is a waterfall diagram, adding up all the reductions. And this is an interesting way of visualizing the results. So One-Click does spit out results in this Sankey diagram. This is one of the graphs that they have. And then I then took that raw data and then used another application to kind of make the graph a little bit prettier. But this becomes a very intuitive way of showing how the results break down by life cycle stage, by the building element, and the high level material categories, and then the sub materials. So even within steel and metals, how much breaks down from rebar, structural steel, and whatnot. And you can show this in a percentage figure as well. So the last one showed you the kilogram in CO2 per meter squared. This one's percentage. And then you can show how this fluctuates by different impact categories as well. So for example, acidification, eutrophication, smog formation, and non-renewable energy. So that's it. That's the results from this project. Thanks.
Thanks, Anthony.
Mm-hmm.
All right, so if you want to stop sharing, then Baha can with his slides. And thanks everyone for starting to add in your questions. I'm particularly excited because I know Baha is going to talk a lot about concrete mixes. So it seems like this is a good crowd. All right, so to give a quick intro, Baha is a high-performance design specialist at ZGF Architects in Portland and focuses on climate-responsive optimizations through quantitative building simulations. He's interested in an integrated approach that leads to a meaningful balance between the quantitative performance and the qualitative essence of design. He is currently leading the lifecycle assessment efforts at ZGF with the aim of workflow optimization, tools development, and whole building environmental impact reduction, hoping that all projects, no matter what scale, should be able to conduct an LCA in an efficient and effective manner. He received a Master in Design Studies in Energy and Environments from Harvard University at the GSD, completed graduate coursework in building technology at MIT, and holds a Bachelor of Architecture from the University of Oregon. And it looks like your slides have slid off, Baha, so if you want to pull them back up.
Hello, can you guys hear me?
Yep.
Sorry, I was having a little bit of technical issues, even though. Okay, can you guys see the slides now?
Yep.
Yes.
Okay, perfect. Thank you so much, Megan, for the introduction. Thank you everyone for joining the webinar. It's a pleasure to be presenting. I'll be mainly talking about two projects here that had the aim of reaching or achieving the LEED material life cycle impact reduction credit through building life cycle, and with a focus on concrete optimization. Okay, so I'm just gonna start by briefly talking about the importance of doing LCA and then why we do LCAs. Basically, the main reason behind doing life cycle assessment is that we build a lot of new construction every year, around 60 billion square feet of building each year. Most of us are familiar with this chart showing how building operations and embodied carbon of the building sector together are responsible for around 39% of global warming emissions or greenhouse gas emissions. When we separate those into building operations and embodied carbon of all the building stock, operations would be around 28% and embodied carbon would be around 11%. But when we look at this a little differently, basically looking at only new construction, imagine on January 1st of 2020, we start with a clean slate and look at everything that we build for the next 30 years. When you add up the impact of all the embodied carbon and the operational carbon in the next 30 years from new construction, they are roughly equal, with 49% being embodied carbon and 51% being operational carbon. And that kind of brings up the consideration that embodied carbon is potentially as important as operational carbon. One more thing about embodied carbon is that when we build a building, there's no chance to undo what we built, basically. So the embodied carbon is locked into place. With operational carbon, you might have a potential to do future optimizations or energy efficiency measures to optimize it. But again, I just want to emphasize that both embodied and operational carbon are as important. One more point or more of an incentive is the changes to LEED v 4.1, where in LEED v4, there was only one path to achieve the credit through the LCA option, which was a 10% reduction in global warming potential and two other environmental impact categories, leading to 3 points. Now, with the changes in LEED v 4.1, just conducting an LCA would give you 1 point, and that would be just, your proposed building. You don't even need to create a baseline model. This is just to get more people consider life cycle assessment and learn about embodied carbon. A 5% reduction would get you 2 points. A 10% would get you 3 points, similar to what we had before in LEED v4. And there's also a path to get 4 points. Now, the challenge with V4 was that sometimes, the process of doing a whole building LCA could be pretty time consuming, and then it was just challenging because sometimes you would do all the process, all the work, and then basically prove that you're not hitting the 10% reduction. So you don't get any points. Now it's more guaranteed with the 1 point for LCA. I'm just going to talk about workflow through two case studies, mainly focusing on one in more detail. The first one is the ZGF building, California Air Resources Board. It's a zero net energy office and lab building with around 420,000 square feet of office and lab. The rendering that you guys see right now is the right lower corner of the building, so you can kind of compare the scale of the whole building to the rendering. The construction material of the building was both concrete and steel, with majority of it being concrete. In terms of workflow, originally, as we've done more whole building LCAs, we've learned, similar to the SFO project, we've learned that doing whole building LCAs as design options is very difficult, especially with large buildings. Maybe with a residential, single family house or something, it could be pretty easy, but with larger buildings, it's just really difficult, especially on the architecture side, to model all your envelope twice. It just literally requires twice the amount of labor. So what we learned is that detaching the models basically and defining work sets would be a good way to optimize your workflow. So starting with the building, it's important to have a good, structural work set. Typically, this would come from the structural engineers and is linked into your Revit model. And then we have the envelope or enclosure from the architects. To create a lead baseline and proposed model, you would need to, or the way we do it, basically, we divide the structure into a baseline structure model and a proposed structure model. And then we do the same with the envelope, doing a baseline model and a proposed model. We then link the two baseline models together and then the two proposed models together to create the lead baseline and then the lead proposed. So we technically have four often typically detached models from the main Revit model. So organization becomes pretty important. The next step would be to identify and optimize or replace high impact materials through doing an LCA of the baseline model. It's important to look at the whole building material life cycle stages, from product all the way to end of life. Let's say you use an envelope assembly that has lower impact, but would be replaced every 15 years, versus an envelope assembly that has a little bit higher impact, but would be replaced every 30 years. As we look at in the California Air Resources building, looking at everything that went into the building, enclosure and envelope, you can see here that the product stage of materials, which is when the material was harvested, processed, and manufactured, is typically the highest impact that we get from all kinds of materials, unless it's a naturally made material. When we look at the same results by type of material, we see how concrete has the largest impact. Even this is again similar to the SFO building. Even though steel was a large portion of the construction, we can still see that concrete had around 70% of the global warming potential. And then, so all the metals that went into the project, a little bit of masonry, insulation would be next, and then glazing and finishes are fairly minor compared to the overall building. When we look at this in a little bit more detail, we see that, of the 70% impact, let's say in global warming from concrete, 46% of it, or 46% of the total, which is maybe 60% of concrete, was from only the Portland cement into the concrete. And that's one that could be potentially optimized, not necessarily optimized, but reduced. So replacing cement for other materials like SCMs. This one, and then we look at where the impact basically comes from in the building. Floors being pretty major, and then structure and walls. So the process would be to identify, optimize, and replace high impact materials. As we talked about, steel and metals are pretty important. Insulation, wood, and concrete. Now these buildings didn't have a whole lot of wood, so steel, insulation, and concrete. Now taking concrete as an example, this is my favorite kind of quote to use from BBC, I think. If the cement industry was a country by itself, and this is just the cement, not the whole concrete, it'll be the third largest contributor to global greenhouse gas emissions after only the US and China. So this kind of shows the importance of concrete, basically optimizing concrete in our mix, in our buildings. And obviously we would love to replace concrete with something that's you know, a lot more environmentally friendly, like mass timber, but not all of our buildings are to that level yet to be able to go to mass timber. So we still have concrete. So it's important to see how we can optimize it. Typically the process starts with getting a ton of concrete mix designs from your contractor, structural engineer, and concrete supplier. And then these would be input into, we use Tally for our whole building and LCA model. So these would be input into Tally, and then they often change. And then you would have to rerun your model, whole building LCA, and this would take quite a bit of time, only to find out on a Friday afternoon at 5 p.m. that they've changed again and they're pouring the concrete. So it's very important to be able to make some decisions quickly. And then our original workflow was missing that, and it was very hard to rerun the whole building LCA every time something changed with such a high impact material too that couldn't be ignored. So we started thinking about sort of a missing piece in between our whole building LCA, and then when we get the concrete mix designs where we could do some quick analysis of concrete, sort of decoupled from our Revit model, and then have the results after that optimization input into our Tally model as the final LCA. What we did is that based on all the lessons that we learned from a few projects, was to create this simple concrete LCA tool with data that comes from Tally. These are based on studies that we ran for different mix designs, and then all the ingredients that went into concrete. And the reason in our workflow, the reason we used Tally data was to keep the same data as our whole building LCA. So it's important for us to be able to re-input it into our whole building LCA and get the same results. Basically, it's a simple spreadsheet. It starts with the proposed mix design. You would you know, select a region and then input all the criteria that you would get from a structural engineer or contractor. Mainly your PSI is important. Again, your region is important, and then all the ingredients inside the concrete. And then the tool, based on your inputs, would go and would find a National Ready Mix Concrete Association regional baseline practice for your concrete. Let's say here we had the Pacific Southwest region, 4,000 PSI, and then it'll find the typical 4,000 PSI concrete for the Pacific Southwest region and compare your baseline to the proposed from the data that we had saved from Tally into the final, into this comparison, and it'll tell you in the 6 main environmental impact categories which one you've shown a reduction, if it's a negative number, or if something's increasing and is more negative. So it'll basically very quickly tell you if this mix is better or worse. A few things that was important for us in this for this tool to do was that to decouple it from Revit and our whole building LCA, so it doesn't require any geometry. It doesn't really require any LCA expertise. Everything happens in the background. You just type your concrete mix design numbers. It's applicable from, you know, SD to CA, you know, very early in the design. If you get a concrete mix design, you could just type it in here, even when you don't know what your floors and columns, how large they are. You could just see it, see how it is. And if a mix is worse than the regional baseline, you definitely want to change it. It helps, it lets you do live LCA of concrete, again, just by typing a number. This point is probably the most important part of it, where it could be used real time in meetings with project partners. Let's say your structural engineer, your contractors, concrete supplier, you just literally type the numbers and could see if something's better or worse, instead of spending hours or weeks sometimes trying to communicate how you could improve it. And then this is also pretty important, focusing on Portland cement content versus SCM. So as the SFO example, or the other example they were both mentioning, it's important to reduce the cement content. We typically only in the last few years, most people only focus on SCM percentage. Let's say a 15% SCM mix. But then when you run the analysis, it's really the amount of cement that drives all the impact. So you could have a 15% SCM mix that has 500 pounds of cement and it's 5,000 PSI. But you could also design, or the structural engineers could also design a 15% SCM mix that meets the same structural criteria, 5,000 PSI with, let's say, 450 pounds of cement. So not every 15% SCM mix is equal, basically. And then we've also hoped to make it pretty simple. So in the future, it could be updated. I want to give a little bit of credit to the leadership at ZGF because even though we spent quite a bit of time on this, we eventually decided that it's more impactful if we give this away to everyone in the industry to use versus us using it in maybe 10 or 20 buildings, just because of the importance of concrete and its contribution to global warming. So we'll be giving it away to other people. In the example again, the California Air Resources board building, by using this tool, we are able to reduce our the amount of cement, only focusing on cement, in our mixes from almost 20.7 million pounds to 16.3 million pounds in the proposed, which was a 24% reduction in cement content. Now, when we run our whole building LCA, because the impact of that concrete reduction is watered down by the amount of steel and all the enclosure and all the other materials that went into the building, we don't get the 20% reduction as a whole anymore. It'll be around 10% reduction in global warming potential, and over 5% reduction in 2 more categories, which led to 2 points under LEED v4.1 for this project. So the final results, we basically only documented the optimization of concrete, and we were able to get the 2 points. Now I want to explain that we also did other optimizations in the enclosure, assemblies, but because of there's a lot of challenges with, as I mentioned, with modeling 2 enclosures in the architectural model, and then we estimated the impact to be fairly small compared to concrete, so we didn't necessarily document those, even though there were other reductions that were considered in the workflow. The second example, which I very briefly talk about, is Department of General Services office building in California again. It's a zero net energy office building, around 400,000 square feet. The difference is that with this one, the majority of the structure was just concrete with very little steel, and obviously all the steel that went into reinforcement. With the same process, we were able to reduce the amount of cement from 15.9% to 11.8%, which was a 25.5% reduction, which led to, as a whole building LCA, this one led to more reductions because we didn't have steel watering down the results. So our global warming was reduced by almost 15%. And then we had 2 more categories, eutrophication and smog formation, reduced by more than 10%. So we were able to get the 3 points under LEED v4.1. Now, something that's pretty important about these 2 is that most of these optimizations in terms of concrete happen just by talking to the other stakeholders, basically the project partners. It didn't necessarily add any cost to the project. Now that our workflow is more defined, we were able to do it even faster, and it reduced the overall building impact by 15% in global warming. So the results are pretty major. Again, I'm sharing this email. This is a little email address that we made just so we can share this tool with you. If you email lca-tool@zgf.com, I can send you a copy of the tool. I'm gonna do a quick overview of the tool as well. Just a quick credit to Tally for allowing us to use their data, even though it's outside their program. They let us use it because they also understood the importance of optimizing concrete in our MCA, also for providing the baseline info. The spreadsheet is very, very easy to use. There's a little instruction tab that would tell you how to use it. the NRMCA regions are pretty important. So just selecting what state your project would be, and then the NRMCA region is listed right next to it. Let's say Pacific Southwest as an example. And then when you go to the mix design tab is where the analysis happens, basically. Anything in yellow is user input, and anything in green is results. Blue would be your proposed, and then orange would be your baseline mix. The first step would be to select your project region, and this is pretty important because of concrete, supply availability in different regions are different. So you want to make sure you're comparing to what's available in your region. There's also the national NRMCA average, which could be used. We often only use the actual regional baselines because, for instance, the Pacific Northwest region has generally lower cement content concrete, and that's a little harder to optimize in some ways. So it's important to consider that. Let's take Pacific Southwest as an example. Let's take Pacific Southwest as an example. So you basically to do a test, you start by application of the mix. So do you use it for floors, columns, or other application? Typically, your structural engineer or contractor would give you a mix design number. It's just for record keeping. This one's pretty important to choose the the strength of the mix, how much, what basically defines the baseline. Let's say if this 8,000 psi concrete with 800 pounds of cement, if we change it to 6,000 psi, which doesn't make sense, obviously the results would change. So it's important to know what strength you're comparing it to for the baseline. And then you start typing your ingredients, cement, fly ash, slag. Coarse aggregate sometimes comes into multiple, sizes. You could just add up all of those here. Lightweight aggregate, fine aggregate, which is typically sand, water, steel reinforcement. This one's pretty important because sometimes you might have the same mix. Let's say you might use this mix for your floors and columns, but the amount of steel that goes into them might be different. So you technically want to look at two different mixes. And air content, which is not necessarily used here, but is used for a different calculation. After you type all of these numbers, the tool would create your baseline mix design based on an RMCA data again, and then it'll eventually compare the results and then tell you if your mix is better or worse in different impact categories. If you need to do a whole building concrete LCA, you are able to do it here. You can basically scroll down and there are more mix designs down below where you could add more mixes. But to be able to do the whole building concrete LCA, again, not all of the building, but just the concrete, you would need to have the total cubic yards of mix for each mix in your building. So let's say you have 200 cubic yards of this mix and then 300 cubic yards of the other mix. And then the spreadsheet would calculate what the average savings would be for the overall. If you keep it at one cubic yard and only do one mix, you could get a chart for only that mix in the chart tab that shows the reductions. If you do more than one mix and and have all the other cubic yards for the total building, this would be for the total building. Yeah, so this was just a quick overview of the tool, and I will stop sharing now. Thank you, everyone.
All right, thanks, Baha. All right, so apologize to everyone. We are running tight on time. We do have until 10:15 if you want to stick around for questions, but we still have one more presentation. So, Toria, if you want to share your screen. All right, Victoria works at Ambient Energy as a sustainability consultant, facilitating green building certifications, performing daylight analysis, and whole building life cycle assessments. She loves wearing many different hats and is always up for a challenge. Victoria fulfills her passion for embodied carbon reductions through completing whole building LCA and informing design teams on how to select better building materials based on their environmental impacts. Victoria holds a BS in architectural building engineering from La Laguna University in Spain, where she focused on structural concrete and building rehabilitation. She also received an MS in sustainable design from Thomas Jefferson University, publishing her thesis on frameworks to reduce greenhouse gas emissions in buildings. She's currently volunteering with the Carbon Leadership Forum as the webinar coordinator. So normally she would be doing the role that I am doing now. So take it away, Victoria.
Hi, and thank you very much, Megan, and thank you everyone who has joined the webinar today. By no means I'm trying to say that this is the right answer. This is just based on about 3 years of my research and doing my whole building LCA for projects. So just as Baja has mentioned already, and you all know, like the building stock market predictions are looking pretty overwhelming, at least by the UN, when they notified us that it was like, okay, by year 2060, we'll have all these square footage added to the built environment, and knowing that that will mean like a one New York City every month for the next 40 years, it does really overwhelm. When we compare it, Baja also has shown this graphic comparing to operational carbon. We can see the importance of the embodied carbon as well. And then there was a carbon positive summit, and Architecture 2030 kind of like presented this scenario for the zero carbon emissions by 2040, and kind of put these interim emissions targets and reductions, and focusing mainly in by 2020 there should be a 40% reductions in embodied carbon, and by 2030 65% reductions, and with the target goal of getting to zero emissions by 2040. So based on those predictions from the IPCC, we have kind of like by 2020, we have a carbon budget of 340 gigatons of CO2. And if we really want to make this happen, if we make 65% reductions by 2030, we have a 67% chance of meeting this goal. Otherwise, if we go to the 2050, we might get down to 50% chance. So when I see these things, it's like, for me, it's very important to really try to standardize, not that this is even possible as of right now, but try to have everybody doing the same thing and creating baselines in the same way. So when you are comparing your baseline and proposed design, then you can say, okay, it's 10% reductions towards this goal of 40% by 2020. So how can we even get there if we don't have a baseline that we can all use? So with LEED whole building LCA, I'm sure a lot of you are familiar with this. If you're a practitioner, you only include building enclosure and structure, and if your structure has any covering or any interior finishes, you need to include them as well. And optional elements for LEED are the interior non-structural walls and interior finishes. However, for example, for ILF5, for the Living Building Challenge, you need to include all these. Let me see. So what LEED requires to be the baseline and the proposed design cases needs to be comparable in size, in programmatic function, in orientation, and in energy performance per the prerequisite. So what that means is that the ASHRAE standard 90.1 appendix G, table 3.1 needs to be taken into account for the building enclosure. And I will go into more details with that. So knowing that, it doesn't really talk anything besides the size, programmatic function, and orientation. It doesn't really talk about the structure much here. It only has a requirement for this because it seems like there is this standard that can be used for the building enclosure. So I'm gonna talk about the building enclosure right now, and what I like to do in early design for determining the baseline is that I go to the ASHRAE 90.1 Appendix G, Table 3.1, and look for my climate zone. Then I do have, well, we have done internally research about the typical assembly types for your climate zone based on the building type. So if I have a metal building, if I have a concrete building, a steel building. So what are the different assembly types that I can use, and what are the different insulation types and thicknesses that will meet that requirement for ASHRAE 90.1. And very important is to coordinate with energy modeler throughout the design for the building enclosure to make sure that you're using what they are using as well. So when you go to ASHRAE, it's like, whoa, wait a minute. If you're not an energy modeler or like a mechanical engineer or a building envelope engineer, it gets a little overwhelming when you go to the table. And this is my color, my ASHRAE 90.1 2010 Colorado Zone 5B, and I go to the assembly minimum and I see all these U factors, and it's like, wait a minute. I have no idea how to put all this together. And it happens the same for the vertical fenestration and for the skylights and all these different elements. So I start having a conversation with the energy modeler, and then I see that, for example, this is what I got from one of our projects, energy modeler. So for different elements, and the standard reference is referencing to the ASHRAE standards and the proposed design, what they actually used. And you can see in both there's a U factor. So from here, sometimes you will get a proposed designs where the U factor is lower than the ASHRAE, and LEED says that you need to use a comparable building enclosure. So then I would recommend that you use the same U factor for both. So what that means is that when I have the final whole building LCA, I create the baseline not based on the ASHRAE 90.1, but based on the proposed design U factors. So that, I'm not saying that you cannot use the assembly standard, the standard assembly that is for your climate zone, but that you change that insulation value to get you to the same R value or U factor for both to have the same. I'm sorry, I need to run through this really quick because we are running out of time. So the structure, one of the good resources out there is the whole building life cycle assessment. It was created by the Structural Engineering Institute and the American Association of Civil Engineers. And it has a good way to start creating baseline. However, it's a little bit more complicated to create a structural baseline because every single structural engineer that I work with already tells me, well, we are already doing everything we can to make this the least amount of steel, the least amount of concrete and everything. So then you start asking more questions to them, and what structural elements can be avoided, and not that I'm going to cut off a column, or but increasing the spacing or moving walls around if you're having CMU walls, like structural walls, for example. What is the typical reinforcement spacing or spacing? Has the slab been reduced or modified? Can you do that? For example, Anthony presented a sample of like the thickness being reduced as well. And and maybe the roof framing or the wall framing can change from metal to wood, or different things that can be done, and then your baseline still will be, for example, in this case, like the metal roof framing, and your proposed case will be the wood framing. Then a big thing that I struggle with is like, what is the recycled content? What is my baseline? And I have had several conversations with the American Iron and Steel Institute. And for North American steel, I have to specify this, that this is only for North American steel. You should never use less than 80% recycled content as your baseline for steel rebar. 80% recycled content for hot roll structural sections, and 25% recycled content for steel decks, steel joists, cold form, etc. You can see it there. So for the concrete baseline, as Baja was mentioning, is a challenge, and is always the cement is the biggest impact. I have found that contacting local concrete producers have been the best resource for us, because, for example, in Denver area, the baseline concrete has 0 to 3% fly ash. So even if the average, the industry average might tell me that is up to 6% the baseline in the Colorado area or the Western region, still the area where I'm working my project on, it is not. So I would highly recommend to do some research on local concrete producers and get their availability to reduce that cement in your mix. And final thoughts, I want to make sure that everybody understands that whole building LCA is not energy modeling. We don't have an exact science, not that energy modeling is even an exact science, but they have more standards and reference that they can apply. Start the talk early in design, and to meet 2020 goal of 40% reductions, and to meet 2030 goal of 65% reductions, we should try to establish baselines and things that they are according to the area where you're working, and what is to like assembly types and things that are happening where you're building your building. Otherwise, you might have 40% reductions, but they are not 100% accurate. Not that even there will be 100% accurate, but try to be real with what you're doing. And that the ECN is a place to share your knowledge and ask questions. So please post to Basecamp, ask questions, and try to everybody will bring an answer, and maybe if not, I don't know, somebody will know the answer. There is a lot of knowledgeable people here, and I'm very happy to share what I know and to receive all the information that you all have to share. So thank you very much for listening.
Thanks so much, Victoria. If you want to stop sharing, and I'll switch to. We have just a few minutes for questions, and I highly recommend, if you have not already been looking in the chat box, we have got a PT tendon EPD that's already come up, and some great questions and answers that have already been coming through. So just to highlight a couple that I've seen throughout the presentations. So towards the beginning, there was a question around one of Raphael's slides about the terrazzo versus linoleum comparison, which I think brings up a point that we haven't discussed, which is how do you account for durability, but how are you accounting for reference life in each of your, you're all using different programs and different approaches. And this is one area I think where you can sort of default to what the program suggests. You can have a conversation with your client. You can use a tool like the recommendations in the LCA practice guide. So if any of you have thoughts on that you'd like to share.
Sure, this is Raphael. And I mean, for the calculations that we showed, we were using the kind of default reference life in Tally, which is a kind of time independent calculation. So if one product has a reference life of 40 years and the other one has a reference life of 20 years, it's going to basically double the values for the 20-year product to say, well, over that 40-year period, you needed to purchase it twice, which on the one hand makes sense, but on the other hand, doesn't include any kind of discounted value for the time value of carbon, which I think is actually a pretty important factor. Right now, reducing carbon is really critical. So if we can use that 20-year material and then 20 years from now, we have to do it again. Quite possibly the factory that makes it will have, be running on cleaner renewable energy 20 years from now than it is now, for instance. And so the EPD for that 20-year product will be improving. Whereas if you use the 40-year product, you only did it once, you got the value that you had today. So if you can defer some of the carbon emissions down the road, that might be a good strategy in that approach. But that's not generally how any of these calculations are done.
Thanks, Rafael. Anthony or Baha, Victoria, do you have any other thoughts on that one? All right, I'm going to take brief silence as a no because of our time limit. So another question that has come up is how scheduling has impacted the LCA reductions on your project. So I think Paul had experience with, particularly when you're looking at cement reductions, how that will change how much time is left to cure. But if any of you have strategies you'd like to share as to experiences where that went well or didn't go well at the broader group.
Hi, this is Baha. Yes, that's been definitely a major concern, and probably one of the reasons behind the development of this tool. Just because sometimes, sometimes contractors have reasonable, needs basically with something changing, and then the scheduling changing or the curing time. Some, cracking could be an issue. So just being able to respond quickly to the changes that are required sometimes. Would be important, which hopefully through a quick LCA of the concrete you could quickly respond if you change the mix design, but it's not as bad or just a little worse. Yeah.
It's worth having this conversation, and a bunch of the commenters pointed out that having this conversation early on and talking through with the contractor what their needs really are is valuable. Foundations are not usually loaded fully for 28 days because it takes a long time to put the building on top of them. Columns can also it's easier to delay strengthening on a column than on a suspended concrete slab. So if you understand why they're in a need for strength, you might be able to, even if you can't get them to use a low cement mix everywhere, you might be able to get it in half of the concrete or somewhere.
Thanks. I'm going to ask one more before we wrap up, which is a couple of the questions have been around, we've talked a lot about concrete, and I think it is one where people have found success in large reductions, and it's obviously something we need to focus on. But what other materials have each of you had experience with when you're doing LCAs that you've been able to demonstrate reductions, or ones that you're hoping to on future projects?
I'll mention, oh, sorry.
Go
yeah, this is Anthony. I haven't done this on a project yet, but I will say that on insulation materials, that can be a huge area. And also, I haven't checked with some of the other software providers, but I think some of the software tools may be underestimating some of the impacts around insulations that use HFCs, for example, as a blowing agent. So like XPS or spray foam insulation. So if you can, those emissions can be quite significant. So if you can kind of steer away from those, there's a lot of reductions to be had there.
I want to add, so for the most part, and sadly it's this way, but there are other elements that they have impact, and as Anthony has said, insulation might be the one of the next ones. However, as of right now, not that I'm saying that is not important at all, but as of right now, if we want to approach like a higher impact in our buildings, we really need to go to the ones that they are producing the highest global warming potential and try to make reductions in those, and then work towards the other ones as well, because they will add up to your total. But I will highly recommend to focus in the big ones and the ones that they have the biggest impact, and try to make reductions there.
I've got three topics I'd like to mention briefly. One is ZGF and ARUP. So Baha and I are working together on a project with a mass timber roof. And mass timber is a really appealing material, but I think the sustainable sourcing of the wood itself is a really critical issue that's not well addressed by any of the EPDs for wood right now. So getting, say, FSC certified wood for mass timber is really important, but you kind of have to do some work outside of the LCA process in order to understand its value and convey that to the project. The second, in that same vein, natural materials are really terrific. We've been partnering at ARUP with the California Straw Building Association to start to look for applications to ramp up the use of, say, straw bale or straw boards and other manufactured products made from agricultural waste that really sequester carbon. So people could start looking into those opportunities. And third, some of my colleagues at ARUP did a really fun comparison of steel space frame roofs, and you can push down weight a tremendous amount and save a lot of material with the space frame design. If you're and on the other hand, space frames are they're not all the same. So it would take a lot. You can if you pay attention, you can do great stuff there.
I want to add last one thing too, for those that they're not familiar or haven't heard yet of the Structural Engineers 2050 Challenge. There's on the Carbon Leadership Forum, you can sign up to join the challenge, and you don't have to be a structural engineer to do so. And one of the exciting things that I think about this opportunity is that hopefully we will all be sharing our findings from our projects and how we have been doing, and we will be able to find benchmarks and maybe determine baselines or different things that have been challenges, and sharing knowledge in this challenge as well. So please check it out if you haven't.
Yeah.
All right, thank you so much. Thank you, Rafael, Anthony, Baha, and Victoria, for joining us today and sharing your knowledge. This concludes today's webinar. Thank you for joining. And if you have any questions or comments, please send them to info@embodiedcarbonnetwork.org, listed here, or post a question on the forum, where you can also find all of the great people who are speaking today. And if you've not yet joined the ECN, you can sign up at this address, the embodiedcarbonnetwork.org. And soon, a recording of this webinar will be available as well on the CLF website. So thank you so much to everyone for joining today, and have a great day.
Thank you, Megan.
Thanks, Megan.
Bye.
Thanks, Jane.
Thank you.
Everybody, have a good day.